start this talk off, I just wanted to mention that in the Numerical Linear Algebra course in the Computer Science department at Purdue, one of the homework assignments earlier on in the semester is for students to write a sparse method for constructing a Poisson matrix, which is a matrix that comes from a discretization of a differential equations problem. I don't want to get too much into the details of the problem just yet, but to give you an idea of one of the applications of the Chroniker product. This 16 by 16 matrix can be generated much more quickly than individually altering every entry of the matrix, which is a solution that a lot of students at the beginning of the semester provide. So just as one motivation, this problem, which comes up a lot in real-world applications, turns out has a lot of exploitable structure if you think of the matrix in terms of the Chroniker product. We'll go through later a much faster way of constructing this and analyzing it once we know what the Chroniker product is. So with that, we'll get into some details on the Chroniker product. So today we focus on defining the Chroniker product and introducing some of its properties, and then we'll show a little bit of how it can be used to reduce the amount of work in performing some matrix operations. So to start, I want to define the product for matrices A, m by n, in B, p by r. The Chroniker product of matrix A and B is the MP by NR matrix that you get by making a new copy of B and then using it as a block in a new matrix with a coefficient from an entry in A. What I mean by that is you take every coefficient in A, multiply it by the entire matrix B, and then use that as a block in a new matrix of much larger dimensions. Okay, so one thing to notice, the number of rows in A times the number of rows in B is the number of rows in the total Chroniker product matrix. And then same thing with the number of columns. You multiply the number of columns. Anytime you define a product, you always want to know what kinds of properties does this product have. Standard scalar multiplication is commutativity, associativity. So we want to know, does that hold for this? And with a first example, we will see right away that no, not all of those properties do hold. Okay. So with these two square matrices, when we form their Chroniker product, first of all, it's going to be 4 by 4 because we're multiplying the dimensions of the two matrices together. The first partition is simply the matrix B times the upper left entry of A. So 1 times B gives us just the matrix B. Upper right block 2 times B gives us this, and then 0 times B gives us a block of zeros, and finally 3 times B. All right, well, what about B Chroniker A? We take -1 times the whole matrix A, and we get this. We take 5 times the whole matrix A, and 0 times the whole matrix A, and finally 10 times the whole matrix A. And immediately we see that the Kronecker product is not commutative. A Kronecker B does not equal B Kronecker A. For example, this entry is not the same. But if you look a little closer, you see that all of the entries are basically the same, just in the wrong place. We've got a -3 in both matrices. We have exactly 7 zeros in both matrices. We have 2 10s in both matrices. So something is going on here. It turns out that A Kronecker B is always related to B Kronecker A by permutations. So not only that, the particular permutations that relate A Kron B to B Kron A, those permutations do not depend on the entries of A and B. They depend only on the dimension of A and B. So for fixed dimensions, M1, N1, and M2, N2, there exist permutation matrices P and Q, so that P A Kron B Q equals B Kron A for all M1 by N1 matrices A and M2 by N2 matrices B. Note the dimensions of P and Q are just P has to be M1 times M2 and its square because it's a permutation matrix. And Q similarly is N1 times N2 by N1 times N2. Both are permutation matrices. In the special case where A and B are of the same dimension and square, we have that P is in fact equal to Q. I'm sorry, P is equal to Q transpose. One fantastic consequence of this fact is that this is a similarity transformation, and so we automatically know a lot about eigeninformation of B Kronecker A and A Kronecker B. All right. So we've seen that A Kronecker B is not a commutative operation, but we're going to look at some of the properties that the Kronecker product does have. For example, given a scalar alpha, the matrix alpha A Kronecker B is exactly equal to A Kronecker alpha B is just equal to the Kronecker product of A and B times the scalar, where this multiplication, alpha times this, is just the standard scalar times a matrix multiplication. We also have associativity of the Chroniker product. If C is some third matrix of any dimensions, then you can move parentheses how you choose. We also have that the Chroniker product distributes over addition. So here we have to assume that A and B are of compatible dimensions to be able to be added together. And you can also distribute on the other side from the left and from the right. You can distribute, in a sense, distribute the transpose across the product. And this next property is important enough that I'll give it a name. Okay. For matrices with compatible dimensions, and I'll say more precisely what that means in a moment, we have the following. First of all, when I say compatible dimensions, I mean if A can multiply with C, and if B can multiply with D. And when I say multiply, I mean in the standard matrix product sense. Second of all, I want to point out this is a big matrix. This is a big matrix, so we're multiplying these two big matrices in the standard matrix product sense. And if A and C and B and D are of compatible dimensions, then instead you can sort of factor through the standard matrix multiplication. And this is one of the first places we're going to see that Chroniker structure, exploiting Chroniker structure, can provide a significant speed up over standard matrix multiplication. So for ease of notation, let all of them be n by n. Okay. Then, if that's the case, we have that each of these matrices is n squared by n squared. I think of that as capital N by capital N. So this multiplication since multiplication is a cubic operation, this multiplication costs n cubed. That is little n to the sixth. And that's discounting the cost of forming the Chroniker products. But those require only n to the fourth, little n to the fourth operations. So doing the multiplication costs n little n to the sixth, forming this. To form this, you just need to take every entry of A and multiply each of them by every entry of B. There are n little n squared entries here and here, so there are little n to the fourth total entries in this matrix. And so each of those costs little n to the fourth, which is dominated by this. Okay, fine. The right-hand side performing this, first of all, each of these standard matrix multiplies here and here is of a little n by little n matrix. So each of these costs little n cubed. Then once you have this n by n matrix formed and this n by n matrix formed, doing the Chroniker aspect of an n by n matrix with an n by n matrix costs little n to the fourth. So the standard matrix multiplies here aren't even the most expensive part of forming this overall. forming the Chroniker itself is the most expensive part. So the total cost of the right-hand side is n to the fourth. The total cost of the left-hand side is n to the sixth. So that's already a pretty big speed up just from taking advantage of Kronecker product structure. Now we assumed all of the matrices involved were n by n, but because this property works for any dimensions, we can also do this in the case that, for example, C and D are vectors. So, for example, if A is m by n and B is p by q and x is if x is n by 1 and y is q by 1, then we can form the product a cron b times the vector x cron y. We can form this in two different ways. The top operation is a multiplication of an mn by an mp by nq matrix times an nq by 1 vector. That costs mp times nq. Then down here we have an mn matrix times an n by 1 vector. That costs mn. Over here, a pq matrix by a q1 vector. That costs pq, assuming that we're just using standard matrix times vector multiplies. Finally, forming the Kronecker product itself requires multiplying all n entries of this vector by all q entries of this vector. So doing the Kronecker product itself costs nq. So the total cost of doing it the smart way is mn plus pq plus nq, which is significantly smaller than the product of all four quantities. In the case that everything is n by n, n by n, n by 1, n by 1, then the difference in costs is n to the fourth compared to n squared. So there's a huge savings by doing operations in a Kronecker way instead of a full matrix way. All right, so now we've seen some properties, we've seen some advantages of the Kronecker structure. We're going to go through some more interesting properties. For example, the eigen-information we can gain via a Kronecker structure. And we'll end with a discussion of a Poisson matrix and how we can exploit Kronecker structure to speed up the process of forming a Poisson matrix. All right, so we want eigen-information via the Chroniker product. Before we get into that, I want to prove a little lemma that we're going to use. So before we even touch eigen-information, if two matrices are square invertible, then I claim the property we were just using is going to allow us to prove that the Chroniker product satisfies a property our brains really wanted to satisfy. I'm really tempted to pull that inverse, pass it through the parentheses, and apply it across the Chroniker product. And it turns out that that's the case, and we can prove it using the property we were just talking about. The proof should be swift and satisfying. Note that A is square and B is square, but we said nothing about the dimensions of A and B, so they can be different dimensions. So I am going to apply the previous property that we were discussing here. We know that A and A inverse are of compatible dimensions. They must be. Same thing with B and B inverse. So we can pass through the standard matrix multiply. We can pass that through the Chroniker product. So this is necessarily equal to A times A inverse and B times B inverse. Each of those simplifies to an identity matrix. But an identity matrix chronicered with an identity matrix is just a bigger identity matrix. How do we know that? Well, by the definition of a Chroniker product, identity just has ones along the diagonal. So when we take any coefficient in this matrix and multiply it by this matrix, we just get 1 times the identity. The next entry of this matrix is another 1. Next entry along the diagonal is another 1 times the identity matrix, just gives us another block of 1s along the diagonal. So we just get nothing but 1s along just the diagonal. And that's exactly what an identity matrix is. All right, with that lemma proved, now we can start talking about diagonalizing a matrix that has a Kronecker factorization. So suppose A is diagonalizable and B is diagonalizable. And lambda and mu are each diagonal matrices of whatever dimensions. I'm using a tall mu for a capital mu. So we'll say B has dimension m by m. Okay. Then we'll see, using that property, that the eigenvalues and eigenvectors, the complete eigen decomposition of A Chroniker B is determined entirely by the eigenstructure of A and of B. I claim that we can diagonalize A Chroniker B as follows. We have Q Chroniker P, then lambda Chroniker mu, and then Q Chroniker P inverse. So first, Q is invertible, P is invertible, just from this diagonalization. Q Chroniker P is then invertible by this property, by this lemma. Using this lemma, we can write down exactly what this is and verify that this does in fact hold. The final step is that this is diagonal, so that we have matrix times diagonal times the inverse of this matrix, which proves not only that this is diagonalizable, but it proves exactly what the eigenvalues of this matrix are. So let's see that in action. First, we can simplify this by passing the inverse across the Chroniker product using this lemma. It's simply Q inverse Chroniker P inverse. When we multiply this matrix with this matrix, Q and lambda are compatible, P and mu are compatible, so we can pass the Chroniker products across, or pass the standard matrix multiplies across the Chroniker product. So we get this. Once again, Q inverse and P inverse are compatible with this and this, based on that assumption. So we can pass the standard matrix multiplies across the Chroniker products, and we get this. And now we see that this equality does hold because we took A and B to have exactly these diagonalizations. So that proves that this statement holds. And finally, just looking at the structure of this sentence, we get matrix equals invertible matrix times diagonal times the inverse of the invertible matrix. It's exactly the form to prove that this is diagonalizable. And now we can look at exactly what the eigenvalues and eigenvectors are. So what we've just proved is if A is diagonalized like this and B is diagonalized like this, then A cron B has eigenpairs, a column of Q, Chroniker, a column of P, Chroniker together, with eigenvalue lambda I corresponding to Qi times mu j, which corresponds to the eigenvector Pj. And we can see that in action as follows. Qi, Chroniker, Pj. So Qi is just the ith column of the matrix Q. Pj, similarly, jth column of P. We can pass the Chroniker, or pass the standard matrix multiply across the Chroniker product and get this, since we took Q to be an eigenvector of A precisely with eigenvalue lambda, similarly for P and mu, we get that this is equal to lambda I Q I Chroniker mu j P j. And finally, since lambda and mu are scalars, we can factor them out of the Chroniker product using a property we already discussed. Qi Pj is exactly one of the columns of this matrix, and lambda I mu j is exactly one of the diagonal entries on the diagonal matrix lambda Chroniker mu. So this completely determines the eigeninformation for A, Chroniker B. Now that we actually know what the Chroniker product is, we're going to return to the Poisson matrix and look at how we can think of it in terms of Chroniker products. Before we get into that, just a little bit of background on where this is coming from. So this differential equation, we're taking the Laplacian of some function and saying that it's equal to some other function on the unit interval, the unit square 0, 1 in the real plane. And the idea is, since functions are continuous objects, to approximate them, we're going to take this 0, 1 square, discretize it, and look at just a grid of points that are inside the square. And then we're going to make sure this equation is roughly satisfied by our solution u on just those grid points. So we're going to solve the Poisson equation, which is the Laplacian of the function u set equal to f. We're going to solve the Poisson equation by finding some function u, and really by find a function we mean approximate a function just on the grid points such that it satisfies this equation on those grid points. And to do that, we're going to use this method of approximating a second partial derivative of our function u. So I don't want to focus too much on these details. We want to get to the linear algebra, but using this method of approximating the Laplacian of a function, we generate an equation, we generate a matrix equation where P is the matrix you see over there, and the dimension of the matrix depends on the dimension of the grid points. So we're solving this matrix equation with a Poisson matrix P, and we're going to recover a vector u that will give us the approximate values of our function u. Okay, so when you're using just a few grid points, as in this case, you generate a small Poisson matrix. But if we, so this is a 3 by 3 mesh, if we increase that by just 1 and have a 4 by 4 mesh, then the dimension of the matrix problem sort of explodes. The idea is to note that this thing has a very specific block structure. I've drawn some dots here to denote where 4 by 4 blocks begin and end. So it looks like each of these squares, each of these off-diagonal blocks looks like a negative identity. Same thing with the superdiagonal. And then each diagonal block looks like a tridiagonal with some structure involved. Just take my word for it. It turns out that you can write a Poisson matrix as a sum of two different Chroniker products, where T is equal to the following. So T is tridiagonal, and I should use T is tridiagonal, and I believe D by D. So over here, P2 is 4 by 4, and that makes sense because this formula presumes that it's going to be a 2 by 2 tridiagonal matrix, Chroniker with a 2 by 2 identity matrix. And yeah, that gives us a matrix of dimension 4 by 4. So this matrix P3 Okay, this matrix is actually P4. Each block is 4 by 4. That means that our T in this context is 4 by 4. So you can see that this term is where we get these negative ones on the off diagonal. because the off-diagonal entries of t are -1s, and in the position of each -1, we're putting an identity matrix times -1. So that's exactly where this is coming from. So P4 over here is this Chroniker and identity, and that's how we're getting the -1s on the off-diagonal blocks. And then when we add to that the identity Chroniker with t, that's where we add 2's on all the diagonal entries, and that's how we get these 2's plus these 2's give us 4's in the diagonal. And then the identity here means that we're placing this block on every diagonal block of P4, and this is where the -1s on the super and subdiagonals come from. All right, now that we've seen the Chroniker structure of the Poisson matrix, we're actually going to look at its eigen decomposition. So, given that we're viewing a Poisson matrix like this, what can we say about the eigenstructure of a Poisson matrix? Keeping in mind how we're defining T. The tridiagonal matrix with 2's on the diagonal and -1s on the super and subdiagonal. Well, for one thing, we know the eigeninformation of this matrix because we already went over that. It turns out that when you have an identity matrix as the secondary part in a Chroniker product, then this structure, identity Chroniker something plus identity Chroniker something else on the other side, that turns out to have a really easily analyzed structure. That brings us to a lemma we're going to use to finish looking at the structure, the eigenstructure of a Chroniker of a Poisson matrix. So let F and G be square matrices, and then consider the following. The claim is that the eigenstructure of M is determined by the eigenstructure of F and G. So let F have eigenpairs xi or xj, lambda j, and let G have eigenpairs yi, mu I. Then the claim is that M has eigenpairs you have to make sure the x and the y match up with the position of F and G. M has eigenpairs yi, Chroniker, xj is the vector, and then the eigenvalue, instead of lambda times mu, now it's lambda plus mu. So we're going to prove that and then use that to completely determine the eigeninformation for the Poisson matrix. So, proving the lemma first. First, we're just going to multiply M by exactly the thing that I claim is an eigenvector. We can distribute this vector across because this is just matrix addition. And the rest of the proof proceeds pretty similarly to the proof that A Chroniker B has well-determined eigenstructure. We just distribute, or let the standard matrix multiply, distribute across the Chroniker product. So we end up with this. And remember, we assumed that X is an eigenvector of the matrix F. And then same thing on this side, we get G times Y, Chroniker, X. Now because this is an eigenvector here and this is an eigenvector here, we end up with, once we factor things out, this is lambda x, factor out lambda. This is mu y, factor out mu. And finally, factor out the vector so that we just have the scalar out front. Okay. Since the dimension of M is just the dimensions of F times the dimensions of G, the number of eigenvector eigenvalue pairs for M would then be the same number, just matches its dimension. So we'll assume F is n by n and G is m by m. Then the matrix M is nm by nm. F has n eigenpairs, G has m eigenpairs. When you combine them like this, there are exactly n times m eigenpairs here. And so that shows this completely determines the eigenstructure of this square matrix. Finally, applying this information to the Poisson matrix, we get that the eigeninformation for the Poisson matrix is completely determined by the eigenstructure of the tridiagonal matrix T. Now it turns out you can even analyze the eigeninformation of this tridiagonal matrix very specifically. If you note, its structure is simply 2 times the identity matrix on the diagonal. That's really just a shift of the spectrum of this matrix. Negative ones on the super and subdiagonal, which is, among other things, symmetric and coplets even. So it turns out that this matrix has very easily identifiable eigeninformation, which is outside the scope of this lecture. We'll cover that later in the semester. But that is how you completely determine the eigeninformation of the Poisson matrix. This, turns out, even has easily determined eigenvector structure. And so if you give me a dimension number for your Poisson matrix, then immediately I can tell you its entire eigenstructure.